Hi everyone. Whenever I see similarities in physics, I feel very happy because it reduces our work, isn't it? So today I'm going to discuss three different problems, but you will see all of them will have similar solution, similar logic and similar mathematics. So here they have given a spring with spring constant K, gravity is downwards, and one end of the spring is fixed to the ceiling. A block of mass m is attached to the spring here. We have to find what will be the extension in the spring, by how much the spring will stretch, extension in equilibrium first, and then we have to find what would be the maximum extension. Now the easier one is to find the first one, because we know in equilibrium the net force, the total force is 0, right? So let's see how to find the extension in equilibrium. So here is the spring. This is the natural length of the spring, the natural length. Now I have attached a block here. Then you know the spring will get stretched. Let's say the spring went up to here in equilibrium. So let me write x naught as extension in equilibrium. Now why will this be in equilibrium? Because one force here is gravitational force mg, and what would be the other force? Remember, it is in contact with a spring, so there will be a spring force, isn't it? And what is the formula for spring force in magnitude? K into extension. What is the extension here? X naught. So if I assume this is the equilibrium extension, or if I assume this is the position where the block is in equilibrium, then the net force should be 0. That means mg should be balanced by kx naught. So what will be the extension x naught? Mg by k. So that would be the answer for the first question, right? Now why this extension in equilibrium is same as maximum extension? Why it is not same? Because when you first attach the block here, when you first connect the block here, what will happen? There will be a gravitational force mg, and what will be spring force at this position? At this position spring force will be 0 because there is no extension till now, right? So if x is 0, spring force will be 0. So when the block is here, so when you first connect the block, there will be gravitational force and there will be no spring force at the start. Let us say gravitational force is 10 Newton. So what is the net force right now? 10 Newton, because this is 0. So because of that, your body will accelerate. And as the body will accelerate, as the body will start coming down, remember it started from here. So as it is coming down, because of the increase in the extension, the spring force will also increase. So let's say it is right now 6 Newton. But what was the gravitational force? It was 10 Newton. Right? So it will further accelerate because there is still a net force of how much? 4 Newton, 10 minus 6. So because of net force downwards, it will further accelerate. So its velocity will further increase. And a time will come when the spring force will also become 10 Newton, same as gravitational force mg. So now what is the net force? Now the net force is 0. Now many students think when net force is 0, the body will stop. How it will stop, students? From here to here, remember it was accelerating. Accelerating means what? It was moving faster and faster. So how you can move faster and stop? Right? It's not possible. So till here our block was accelerating faster and faster because till this point mg was greater than spring force, right? So here it will have maximum velocity because it will be moving faster still here, because till this point it was accelerating. Now what will happen? Because it has velocity, it will further continue even if force is 0. Newton's first law, right? Even if force is 0, if you have motion, because of inertia, you will continue. When pendulum comes like this in the mean position, it doesn't stop. Even if force is 0, it continues, right? So this block will further continue. Remember this would be your extension in equilibrium, which we already calculated. Then it will further go down, and when it will reach here, let's say, your spring force will become even more than 10 Newton, because your x is now even more than this x naught. So your spring force will become even more than 10 Newton, let's say 14 Newton. Gravitational force, which is weight, is 10 Newton only, right? It depends only on mass. So now what is the net force? 4 Newton. In what direction? Up. But our body is coming down. So when our body is coming down and force is up, it will move faster or slower. If you are running this side but force is this side, opposite, you will move faster or slower? Slower, right? So from here onwards, our body will start moving slower and slower. Till where it will move? It will move till it will come to rest, right? And from there, that time the spring force will be even more than 14. Maybe it is, I don't know, let's say 18 Newton. And here, what is the gravitational force? It is fixed 10 Newton. So now, because of net force, how much? 18 minus 10, 8 Newton upwards. Because of net force, it will now go up. But till this point, it will come, right? And that is the point where velocity is 0. And that extension is your maximum extension. Now, those who know simple harmonic motion, you know this is the mean position, right? Because this is where the velocity is maximum. Here, remember, it started with 0 speed. So this is one extreme position and this is one more extreme position, isn't it? So this is basically the amplitude, right? So basically our block will oscillate this way. So if this is the equilibrium extension or extension in equilibrium, then what will be the maximum extension? This will be also amplitude x naught. So maximum extension will be simply twice of x naught, which would be equals to what was x naught? Mg by k. So if you know the extension in equilibrium is x naught, which is very easy to calculate because in equilibrium net force is 0. What will be the maximum extension? Twice. Simply double of that. That you can understand if you know simple harmonic motion. Otherwise, I will try to show you the same answer using work energy theorem. So if this is your spring, when it is not connected to any block, and then when you connect a block, it will stretch, and let's say it has come up to here. Up to here means what? This is your maximum extension, right? And at this point its velocity is momentarily 0. Let us call this point as initial and this point as final. So from initial to final, we will apply work energy theorem. Now what work energy theorem says? Work done by all the forces on the body is equal to change in kinetic energy of the body. Now from here to here, when the block starts from here to here, what are the work dones? Well, for that you should know what are the forces. So here mg will be there, and as it comes, spring force will also start acting. K into x, where x is the extension, right? So let us ask work done by gravity first. So let us divide this work done as work done by gravity plus work done by spring, and change in kinetic energy is final kinetic energy minus initial kinetic energy. Remember, we are not assuming any air resistance. Now from here to here, gravitational force mg is constant and it is downwards. and displacement from here to here is also downwards. So gravity will do positive work, right? What will be the work done? Force into displacement. So mg into displacement is x max, right? Now what would be the work done by the spring? Remember, spring force is variable, so we have to integrate. That integration is very common. You all must be knowing that the work done by the spring force, if you integrate, just if you want to know the magnitude, is kx dx. So this is the force and this is dx. If you integrate from here to here, 0 to x max, k will come outside. Integral of x dx is what? X square by 2. Upper limit if you put, you will get x square by 2 max. So very common result, right? Work done by spring is half k x square, and here we are going from 0 to x max. So this is the work done by the spring in magnitude, just the modulus. Now sign how to find. Understand, from here to here spring force is up, isn't it? And displacement is down, so work done by spring force will be minus, and the magnitude we know, half k x square max, right? So this is the work done by gravity, work done by spring. Now what is the final kinetic energy? When it reaches here, it momentarily stops because we want to calculate maximum extension. So final velocity is 0. If velocity is 0, kinetic energy is 0. And when it started, initial velocity was also 0, right? We just released the block. We have just released. So it starts from rest. So initial kinetic energy also 0. So now if you take this one that side, you will get mg x max is equals to half k x square max. You can see 1 x max will cancel. So what will be x max? If you cross multiply 2 mg by k. Same result, right? So now question number 2 is similar to the previous one, but this time the spring is kept horizontally. So now gravity will not pull the spring, because now gravity here will be balanced by the normal force, isn't it? So now there is a block attached to the spring, and we know it will not be pulled by gravity downwards because normal will cancel gravity. Then how it will be extended? Well, this block also has some charge, Q. So what we will do, we will apply a uniform electric field towards right. So we'll switch on a uniform electric field. Let's say the value is capital E in magnitude. So once it is switched on, this will feel a force because of the electric field, right? Electric field is the region where a charge feels a force. So because of this electric field, this charge will feel a force this side if it is positive charge. And therefore, as it goes this side, we have to find the equilibrium extension and maximum extension. So what will happen? The moment you switch on electric field, this was the starting position of the spring, and let's say the spring will start getting stretched, and let's say it reached till here. And at this position, let's say the net force is 0. Net force 0 doesn't mean it is at rest, remember, because it was already moving. So in fact, this is the position where velocity is what? Maximum, right? So here, when the body is in equilibrium, what are the forces? Well, this side there will be electrostatic force, which is equals to Q into E, because E is given, isn't it? And there will be spring force this side, because when the spring is stretched this way, spring force will be this way, opposite, right? So this will be your spring force, and in equilibrium, spring force should balance your electrostatic force. Let me call it Fe, E for electrostatic, and spring force is Kx. Right now we want equilibrium extension, so Kx naught, and now the force is no longer mg, that mg is replaced by what? Qe, right? So what will be the equilibrium extension? Qe by k. So the answer of this is Qe by k. And if I ask you what will be this, without wasting time, twice of this, right? And you can try to prove this using work energy theorem. Now let's see the last problem. So we have a pendulum whose bob has mass m and we have given a charge q to the bob of the pendulum. At t0, a uniform electric field capital E is switched on, let's say in the right direction. Okay, so in this direction, we have switched on a uniform electric field. So because of the electrostatic force experienced by this bob due to its charge, this pendulum will deflect, right? It will go this side because of the electrostatic force. So we have to find the angle made by the string with vertical in equilibrium, and then we have to find, like the previous two questions, the maximum angle made by the string. So let's see how to do it. So because of the electrostatic force, our pendulum will feel a force towards right side, right? So in equilibrium, when the pendulum is here, let's say at angle theta naught with vertical, the net force should be 0. So let's see what are the forces on the bob of the pendulum. There will be obviously gravitational force mg, and because of electric field E, this charge will feel a electrostatic force Fe, which is equals to Q into E, and then there will be a tension force here T, which is along the string away from the body, right? Now tension is at an angle, so let us take components of tension. So one component of tension will be here and one component will be here. To know which is cos or sine, we need angle. Well, if this is theta naught, this angle is also theta naught. So this component of tension will be T cos theta naught, and this will be T sine theta naught. T sine theta naught. So once you have taken components, you can forget about this T now, isn't it? So who will balance this force? T sine theta. And who will balance mg? T cos theta, right? So along this axis, T sine theta naught will balance the electrostatic force Fe, and T cos theta naught will balance the gravitational force mg. We want angle, so we don't want T, so let us divide the two equations, right? So if you divide the two equations, T will cancel. So now sine by cos will give you tan theta naught equals to Fe by mg. This is a very useful equation which will come in many places. Okay, so try to remember this. So when the pendulum is in equilibrium, tan of this angle made by the string with the vertical is always equals to Fe by mg. Try to remember that, okay? Fe by mg. Fe by mg. So now tan theta naught will be what in this problem? Electrostatic force here is Q into E by mg. So the answer will be tan inverse QE by mg. What would be the answer of the second one, the maximum angle? Well, without wasting time, you can tell it will be twice of this, right? Twice of tan inverse QE by mg, isn't it? Twice of tan inverse QE by mg. But for this particular case, let me try to show you how it comes. Okay, then you will appreciate the beauty of this formula. So when our pendulum will go to maximum angle from vertical, let me call this angle theta m, m for maximum, we know the velocity of this pendulum will be 0 momentarily, right? So here you should not balance the forces. Balancing forces will be always in equilibrium, remember. So how to do this? Well, just like we used work energy theorem, same thing we have to do. Remember, our pendulum started from here. So this is our initial position, and you can clearly see this is the displacement. This is the displacement, S. Now you can take two components of displacement, one here. Okay, let me call this component X, and one here. This component would be Y. So X and Y are components of your displacement of the pendulum from initial position to final position. So let me remove this because I know the components. These are the components. Now, what are the forces on the pendulum? Well, here one tension will act, that we already know. So as our pendulum is going this way, we know there will be a tension force T. But if you notice carefully, this tension force and this displacement, the small displacement along this path, if you notice carefully, this tension and this small displacement, this tension and this small displacement, this tension and this small displacement, all are what? Perpendicular. So work done by tension in this problem is 0. Very good. What about work done by gravity? Let's try to see that. Now from here to here, the gravitational force is mg, which is a constant force. And if force is constant, we don't need to do integration, right? So this is the force, and from here to here, the displacement is this and this, right? Now you look carefully, this force is perpendicular to this displacement. So no work will be done in this part by gravity. So gravity will only do work in this part. So work done by gravity will be force mg into displacement along the line of gravity, which is y. But remember, displacement is up, gravity is down, so we have to put minus, because in work done cos 180 will come, right? Angle between force and displacement. That's why minus. Now, what is the other force that is doing work? Electrostatic force. And remember, charge was Q and electric field was uniform like this, right? And since charge is positive, electrostatic force will be this side only. So electrostatic force is this side, QE. Now check carefully. This is also constant force, so no need to do integration. Now look carefully. For this force, this displacement is useless because this displacement is perpendicular to this force. So no work will be done by this force in this displacement. So the only work will be done in this displacement, right? And you can see this force and this displacement x are in same direction. So work done by electrostatic force will be force QE into displacement. So this is the work done by all the forces. Now our pendulum started from rest, right? Initially it was at rest and then we switched on electric field. And then as it went, when it reaches maximum deflection, their velocity again becomes 0. So now let us use work energy theorem. Work done by tension plus work done by gravity plus work done by electrostatic force will be equal to change in kinetic energy. This is 0. This is also 0. This is also 0 because initial velocity, final velocity is 0. Work done by gravity is minus mgy and work done by electrostatic force is QEx, that is equal to 0. So from here what will you get? QEx will be equal to, this will go that side, mgy. Now look carefully, this y and this x. So if I draw this line, then this x will be this x itself, right? Okay. Now how to find x and y in terms of this theta? That you have to see carefully. So we have reached till here. Now how to bring theta in this equation? Look carefully. If you look at this right angle triangle, let us call this hypotenuse, the length of the string as L. Then what will be this side? This is adjacent side, right? So adjacent side is always hypotenuse into cos of angle. And this side is what side? Opposite side. So this side will be hypotenuse into sine of angle, isn't it? So this x is nothing but L sine of angle, and this y, if you look carefully, if this is L, then this is also L because this is the length of the pendulum, right? This pendulum only went from here to here, no? So if I continue this side, this length is what I am saying is L. So this is L, this is L cos theta. So this part which is y will be what? This y will be what? Think again. L minus L cos theta. theta m. Then I can take here L common, 1 minus cos theta m. So if I substitute this x and this y, what will I get? QE. What is x? L sine theta mg. And what is y? L 1 minus cos theta. This was the previous answer for theta m. L will cancel. So this is QE. Now look carefully. This 1 minus cos theta, you need to simplify. Now 1 minus cos theta, you must know, is 2 sine square theta by 2. Okay, 1 minus cos 2 theta is 2 sine square theta. 1 minus cos 2 theta is 2 sine square theta. So 1 minus cos theta will be 2 sine square theta by 2. And sine theta, therefore, in half angle can be written 2 sine theta by 2 cos theta by 2. So this you must know from trigonometry. So when you substitute these two here, this sine theta by 2 and 1 sine theta by 2 will cancel. So you will get QE. What is sine theta? 2 cos theta by 2 equals to mg. What is 1 minus cos theta? 2 sine square theta by 2, but 1 sine got cancelled. So 2 sine theta by 2. 2 cancels. So now mg you bring this side, cos you take this side. So what will you get? QE divided by mg. Let me mention here. So QE divided by mg. Okay, this mg I brought here. You cos you bring this side. Sine by cos will be what? Tan, but this is theta by 2, remember. Remember this is theta max. Okay, I felt bored to write this m. Okay, so this is m actually, theta m everywhere, isn't it? So now what will be theta m by 2? Theta m by 2 will be tan inverse of this, tan inverse of QE by mg. And now if you cross multiply 2, you can see it is the same result. So this is much better to do because this takes a little bit of time, isn't it?